Now imagine the scenario that you come to school one morning, right? And your friend is just horribly sick. They look like they have the flu, right? They don't look well at all. And now, you're spending time with this person. They're coughing all over the place, right? Somehow or another, some of their germs land on you. Okay, now you've got nothing. You're feeling just fine. A few hours go by early afternoon, you're not feeling right. Something's not right. Okay? So you kind of wait it out a little bit. You go home, things start to get worse, and by early evening, you're done. You have whatever your friend had, right? You're now ready for bed. You've got the shivers. You've just got the flu. Okay? So what happened? In the morning, you had nothing. You had none of the germs on you, right? You got a few of them from your friend. They began to multiply at an increasingly faster rate, okay? And now you've got trillions of them in your body, okay? So within a matter of hours, you went from having no germs to having trillions and trillions and trillions, right? So there was incredibly quick growth, right? And over a very short period of time. And this is an example of exponential growth, right? Where something changes very, very quickly. So, all right, so that day goes by. The next day, you're still not feeling very well. You go to the doctor. The doctor takes one look at you and says, yep, this is antibiotics time. So they prescribe some antibiotics. You start taking the antibiotics, and you know what? Within a day or two, you feel just fine. So what happens? Again, in a very short period of time, all of that bacteria that had increased in your body now just dies back down to zero. All right? So we had exponential growth and then exponential decay all in 1 week, right? Okay, so that's what we're going to talk about in this chapter, and you're going to see that there are millions of applications of exponential functions. So we're going to learn how to graph them, how to manipulate them, and then how to apply them in problems. Okay. Well, first of all, what do the functions themselves look like, right? They have the form f of x equals b to the x, where b is a constant. Until now, you're used to seeing a variable and a number for an exponent. Now we're going to change things around. The base is going to be the number, and the exponent is going to be the variable, right? So something like that is an exponential function. Now, an exponential function is exponential growth, all right, if this value of b is greater than 1. All right, so for example, 2 to the x, 5 to the x, 7 to the x. And it's not just b is greater than 1. The absolute value of b is greater than 1, right? So we strip it of the sign first. And it's exponential decay if the absolute value of b is between 0 and 1. Okay? Now, one important characteristic of exponential functions is that their graphs always have an asymptote, right? So what is an asymptote? An asymptote is a line that the graph comes exceedingly close to but never touches. That's what an asymptote is, all right? And yeah, it's right here. It's a line that the graph comes exceedingly close to but never touches. Okay? All right, so let's take a look at exponential growth. All right? So the parent function is like this, b to the x, where b is greater than 1. So first of all, let's take a look at some examples. So suppose you have y equals 3 to the x. Would you say that's growth or decay? Growth. What if you have y equals 1 over 2 to the x? Is that growth or decay? Decay. So the first one was growth, This is decay. What if you have y equals negative 1 over 2 to the power of x? This is decay. What if you have y equals negative 2 to the x? It's growth because we have to take the absolute value of it. And now what if you have y equals 3 to the power of negative x? Okay, so let's think about that. What does it mean to have negative exponents? Let's change it to a positive exponent. This is 1 over 3 to the x, right? To make it a positive exponent, which I can also write as 1 over 3 to the x. So now that's decay, right? So the negative, you have to sort of reconsider. So what if I have 1 over 5 to the negative x? This is growth, right? Because it'll be 5 over x, so it's growth. All right, questions? Yes. All right, exponential functions look like this, where it starts off close to 0 and then it increases very, very quickly. So if you look at this part of the exponential function, right here, all right, so this is like x equals something. Now, if we go over just a little bit in the x, right, if you just go over that much, look at how high we went up on the y-axis, right? We go up a lot more on the y-axis than we would have if this was not an exponential graph, right? Like, for example, for a linear graph, right? If I go over 1 unit, I would go over, like, you know, a comparable amount. But here, as the function progresses, if I go over a tiny little bit, I go up so much more in the y. So look, here, I went over a little bit, and I went up this much. Then I went over a little bit more, even less actually, and I went up a little bit higher. So as you move along the graph, going over on the x-axis will give you a much higher change in the y, right? That's the characteristic of exponential functions. And let's not forget that there is always an asymptote, a horizontal asymptote that you always need to put on there. Now, what does the domain look like here? Are there any breaks or gaps? Are there any x values for which there doesn't seem to be a graph? No. So this is important. The domain is all real numbers, always. Okay? You don't even have to think about that one. The domain of any exponential function is always all real numbers. Free points. Okay? All right, and like I said, it has an asymptote, and we'll talk about range in a little bit. Yes?
So for the range?
Yeah.
It never reaches the
right.
axis. It's not
asymptote, yeah.
It's not necessarily all positive.
So it'd just be y.
Yes, it is all positive numbers because it's just not 0.
Oh, I see. But so there's always going to be a number on the y-axis that's lower than where it is. It would be like 0.1. It always, like, for example, like, over a certain amount, so we got half and like.
That's the asymptote, yeah.
So wouldn't it be
But
y
that's
is greater than the asymptote?
Right. Y is greater than the asymptote. He just hit it.
That doesn't mean all real numbers, does it?
Huh?
That doesn't mean all real numbers.
No, never all real numbers. In this particular, you know what? Let's.
When it's greater than the asymptote, it doesn't necessarily mean all positive.
It does, because the only thing it can't hit is 0. It could hit even like a hairline above it.
But then there's still the number below the hairline.
No, it's 0. It comes very, very, like, atomically close, very close, but never touches it. There's never. Yes. I just put the asymptote in green. Okay, so let's do an example here, and you'll see what we're talking about. Okay, now, we're going to graph 2 to the x, all right, using a table of values, and it says to identify the asymptote and the y-intercept. All right, so the default case, this does not have any vertical translation, right? The default case is that the asymptote is always the line y equals 0. Okay? Y equals 0. That's here. That's the default case. That's always going to be the asymptote y equals 0 unless there is a vertical translation, which we'll come to in a little bit. Now, the y-intercept is when x equals what? It's when x equals 0, so it'll be f of 0 equals 2 to the 0, and that's what? 1. So f of 0 equals 1 is the y-intercept. Now, let's use the table of values. Now, as a rule of thumb, this isn't set in stone. As a rule of thumb, is this growth or decay? Growth. When I have a growth equation to graph, I always pick these numbers, all right? Because you always want to pick some positives, you always want to pick some negatives, you always want to pick the 0. If the numbers get too big after the x equals 2, then your y values get way too large, and numbers less than -1 will be way too small. So these I feel are pretty good. Okay, so here we're going to have 2 to the -1, which is what? 1/2. 2 to the 0, we just said was 1. 2 to the 1 and 2 squared are 2 and 4. Now, the first thing you do when you're graphing this is you put the asymptote, all right? It's just like if I ask you to draw anything, anything like a cat, right? In order to distinguish a drawing of a cat from a drawing of something else, there are some, what are some characteristics that would leave no question that, okay, this is a cat? With the ears, the whiskers, whatever, right? So if you're graphing an exponential function, the asymptote is one of those characteristics, okay? So I have to put the asymptote here. Now, I know on the test you're using a pencil and it's a solid line. It's fine to go like a hairline above it. Just make sure I see it. Most of the time you guys are okay with that stuff. Okay, now when x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. Now, when I'm checking graphs for these, you're definitely going to get points allocated for the asymptote. You're also going to get points allocated for extending the graph past the dots. This is not connecting the dots. I want it to look like an exponential graph. So just doing this is no good, right? I want you to extend it here and make it look like it's following the asymptote. And here, you want to go up the curve and it's going to go up rapidly, right? So here, in reality, this is going further and further and further and further and further and further down until they're very, very close to touching.
So should we just draw a hairline as well?
Yeah, just make sure you don't touch the asymptote, but go very close to it. Okay, so what's the domain of this? All real numbers. Now, the range, y is greater than, not greater than or equal to, what? 0. So it's always going to be either y is greater than the asymptote or y is less than the asymptote. Plain and simple, okay? Transformations work the exact same way, right? So where you have x minus h, h is the horizontal translation, and it goes against the sign. K is the vertical translation, and it goes with the sign. A, just like always, is the orientation and the shape. So if A is less than 0, if you have a negative A, what does it do? Reflects around the x-axis. And the value of A is the vertical compression. So for example, if A is greater than 1, so for example, if you have y equals 3 times 2 to the x, as opposed to 2 to the x, This is a vertical stretch, right? It's like somebody is pulling it up, so it goes up even faster. If a is between 0 and 1, so if you have y equals 1 over 3 times 2 to the x, it's like somebody's pushing down on it, so it goes up less quickly, okay? All right, let's graph these then. Now we have not 2 to the x, but 2 to the x minus 2. So what does that minus 2 do? Everything is going to move down. The graph will move down. The asymptote will move down. So what's the asymptote now? Y equals -2. If you just say -2, it's no credit. Okay? -2 is a point. The asymptote is a line. Y-intercept, f of 0 is 2 to the 0 minus 2 minus 1, right? Okay. So this is growth again, so I'm going to pick -1 to 2 for my points. Oh, and this, I always copy and paste, and then these always come out wrong. And I do it every time, yeah. Mm-hmm.
The part that never touches the
Mm-hmm.
becomes it never touches
Mm-hmm. Mm-hmm. All right. So 2 to the -1 minus 2 is going to be 1/2 minus 2, -1 1/2, so -3 over 2, right? 2 to the 0 minus 2, we just said was -1. 2 to the 1 minus 2, 0. 2 squared minus 2, 2. My asymptote is at -2. And at -1, we're at -1 1/2. 0, we're at -1. 1, we're at 0. 2, we're at 2. There we go. Okay? What's the domain always? And the range? Y is greater than -2. And could I have figured out the range before even graphing, before even doing any of this? Just from that? Right? Okay. All right. So here, what's the asymptote? Y equals 0. What's the y-intercept? One half. So I say, let's get used to this notation for y-intercept. F of 0 is 1/2. Now, I'm going to skip this for a minute. What's the domain? And the range? Y is greater than 0. It's always greater than the asymptote. Okay? Yeah. You plug 0 into x. So it's 2 to the 0 minus 1, 2 to the -1, which is 1/2. 2 to the 0 minus 1 is 2 to the -1 is 1/2. All right, so here it's going to be 2 to the x minus 1. So it's going to be 2 to the -2, which is what? 1 over 4. And here we just said was 1/2. 2 to the 1 minus 1, 1. And here, 2, right? Okay, so my asymptote is here. And let's graph. Can we graph this? -1 to the 1/4. And then 1/2. And 1. And 2. There we go. Okay. Huh? Yeah, I mean, it's not going to be NASA precise for these 1/4 and the, 1/6, but we do the best we can. Okay. All right. So what about exponential decay? Exponential decay, it's less than, b is between 0 and 1. So the graph looks like this. So remember, in decay, right, you start off with a high number and then it levels off to 0, right? So decay levels off to 0. Well, close to 0. Okay? So like the bacteria in your body will die, but do you know that you killed absolutely every single one? No, right? Right. So it comes, okay. Now, okay, again, domain is all real numbers and so on and so forth. Okay, so let's graph this function. Now, when it's decay, rather than going from -1 to 2, I pick -2 to 1 because the numbers just work out so much better. What's the asymptote going to be here? And the y-intercept? Right. 1/5 to the power of 0 will be 1. Like here, 1/5 to the power of x, 0. Anything to the 0 is 1. Okay, so let's do these. 1/5 to the -2 is really what to the what? 5 to the power of 2, which is 25. And already that number is too big. 1/5 to the -1 is 5. 1/5 to the 0. And 1/5 to the 1 is 1/5. So here we have the asymptote. And we have -2 is 25. I don't need to graph that one because it's too high. -1 is 5. 0. And 1 is 1/5. Right now, I know that at -2, it's going to be at 25. So when I bring this over, I sort of take that into account and I don't hit that -2. There we go. Okay, this is really steep. Okay, so what's the domain? And the range? Less than? Greater than 0, because it's above the x-axis. Yes, it's decaying, but it's above the x-axis. Yes. So look at this one. What does that +2 do to the graph? So what's the y-intercept? What's the asymptote? Y equals 2, right? And the y-intercept is f of 0, which is -4 to the 1/2 to the times 1/2 to the -1 plus 2. How much is that? This is -4 times 2 is -8 plus 2 is -6. Right, f of 0 is -6. Okay. I copied and pasted and I shouldn't have. Because we plugged in x is 0. Right? Okay. So this is wrong. It should say that one, -4, 1/2, x minus 1 plus 2. All right. So this is going to be -4 to the power of 1/2. -3 is the exponent plus 2. Right? So look, this is -4 times 8, which is -32 plus 2 is -30. -4 times 1/2 minus 1 minus 1 is -2 plus 2. So, -4 times 4, -16. Right, plus 2 is negative 14. Okay, and at 0, we already got negative 6, and here, negative 4 times 1/2 to the minus 1. I'm sorry, 1/2 to the 0. Plus 2, so that's negative 2, right? Plus 2 is 0, is that right? Yeah. Now, it was negative 4 times 8, negative 32, plus 2 is negative 30.
Yeah, it should be negative 2.
So, oh, no, it's, sorry, it's negative 2, because this is the 0. So it's negative 2, you're right. Okay, so the asymptote we said was y equals 2. Okay. All right, I'm gonna go, yeah, I'm gonna go from the bottom up. So when x is 1, y is negative 2. When x is 0, y is negative 6. When x is 0, y is negative 6. Okay, so look, these two are useless to me because I can't, right, they're too far down. But look, so I don't know what's happening here, right? So remember I said before, this is not set in stone. It's just a nice, helpful guide. So I know what's happening here. It's going down, but I don't know what's happening to the right of this. So what I'm going to do is I'm going to add in a few more points, right? So when x equals 2, what's the value here? 0. So when x is 2, y is 0. And then when x is 3, how much is it? Is it 1? Okay. So now, look. It looks like this. Does that make sense? Okay. Now, what's the domain? And what's the range? Y is less than 2. Okay? Well, yes, because here you know that it's going down, right? And it's going to level off somewhere by the asymptote. Okay? All right, so equations for exponential growth and decay when it comes to problems. So exponential growth or decay, sometimes in like real life situations, something either grows or decreases exponentially by a fixed percentage over a specific amount of time. So for example, a car's value, let's say, right, decreases. So a car depreciates in value, let's say, 15% every single year, right? And it's a set amount, right? So if you bought your car in 2016, you know exactly how much it's going to be worth in 5 years because it decreases by a certain amount. For these, or when something like a population is growing by 20% every single year, for these cases, right, we have these equations for exponential growth and exponential decay. And you can see they look very similar, okay? In both cases, you have n equals n subscript 0. We read that as n naught, and it means initial, right? So n equals n naught, 1 plus r to the power of t. So what do all these mean? N is the final amount. N naught is the initial amount that you start with. T is time. It's usually in years. R is called the growth or decay factor. That's what it means, growth or decay factor. And it has to be in decimals. It's the growth factor or the decay factor. Actually, you know what? No, that's wrong. I don't know where that came from, but R is not that. I don't know where that's from. I have to check if that's how they say it in the book, because if they do, it's wrong. R is the rate. Okay? 1 minus R or 1 plus R is the growth or decay factor. All right. The minus is decay. The plus is growth. Okay. So let's take a look at this. The first U.S. census was conducted in 1790. At that time, the population was 3 million, Since then, the U.S. population has grown by approximately 2.03% annually. Draw a graph showing the population of the growth of the U.S. since 1790. Okay, so let's just write down what we're given here. All right, so the U.S. Census was conducted in 1790. So at that time, this was the population. Oops. Right? What value is that? Which variable is that? That's your N naught. 3,929,214. Okay? And we're given 2.03% annually. That's your rate. So R, though, is that divided by 100, so 0.0203. Okay? The equation is N equals N naught. Now, this one, it's for growth, right? So it's going to be 1 plus R to the power of T. And this is 3,929,214. 1 plus 0.0203 to the power of T. We leave T as a variable because we're going to graph it. So finally, N is 392,9214. Oh my. Just T. I leave it as T because I want it to be in variable form. Right? So it says draw a graph. In order to draw a graph, you need two equations, an X and a Y, an N and a T. Okay? Showing the population since 1790. So this is what I'm going to graph right now. Okay? Let's go to our calculators. We're going to plug that in. So instead of T, we're going to put in X. Yes. Yeah. All right. Now, when we graph, are we going to see anything? It's to the left. You can't see it. So we graph, but we're not going to see anything, right? Because my X and Y are set to -10 to 10. In this case, what does my x-axis stand for? Is it okay? So what are the variables in the equation? N and T. Which one of those is the independent variable that goes on the x-axis? It's T, right? So the x-axis is T, and the y-axis is N, and N is the what? The population, right? Where does the population start? At 3 million, blah, 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 blah. So I need to modify my window, right? I need to modify my window for the y-axis. I'm surely not going to need any negative numbers because that would mean a negative number of people, right? So what's a good one to start with? Like what window do you think I should start, huh? At the start of this problem, how many people were there? 3 million, blah, blah, blah. So that's pretty much where I want to start. Okay? So, well, formula would be too much. So a little bit under. So 3,900,000. And where should we go? Y min? But that would mean you have negative that many people. Y min is just the lowest number that your graph is going to go to. Okay? And well, yeah, we're gonna make the x bigger in a little bit. What? You know what? Let's put the y max to. Let's do this. Let's put the y max to 400 million. Yes. No, I mean 400 million. How many zeros is that now? Because this is gonna grow. Did I put the right number? Okay, so 400. All right, and what I'm gonna do is here actually I'm gonna put it to 0. So let's go from 0 to that. Okay. And if this is 1790, how many years ago is that? So t, right. So the time starts at 0, and how many years are we gonna go? Like, let's go to 250 years. Okay. Now let's graph. Look at that. Okay? All right. Now.
You don't have to change the, or you just have to make the x 0. You just have to make the minimum x 0.
Yeah.
Oh my god.
Okay, so look, in my graph, right? So I draw my graph accordingly. Look, I don't need any x's, I don't need any negative values. So this is t in years, and this is n. Is that right? Okay. Now, I go to 400 million, right? I'm going to 400 million. So, how can we calibrate this, do you think? This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 spaces, right? How can I calibrate this? If I'm going from 0 to 400 million, how can I calibrate it? Huh?
20 million.
20 million? Okay. So here's what we're going to do. Hang on. Give me 1 second. So, right, so this is going to be 20 million, and then 40, and then 60. Does 20 million work?
In the millions.
Yes. So here, this is going to be n in millions. This is 0, and then it's 20. Now look at what we're going to do. So if this is 20 as well, right? Let's go by 10 years, right? And so on. Now, look at how we do this. Everybody look. Press trace. Okay? Now, I want to know when the x value is 10, what's my y value? So type in 10, and it's 48 million, right? So I put a point at 48 million. I'm eyeballing here, right? At 50, how much is it? How much is it at 50? 107 million. Okay, at 100. 293 million. Do you see how you can then make your graph? $10, $20, $30. I'm going up by tens. Yeah. Okay. So I'll look at your calculator in a minute. What I want to look for is that at t equals 0, this is at the right place. Yes. 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 Okay. Yeah, there is very little. Okay. So I'll look at calculators in a minute. Let me do this one. A cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of the caffeine from their system per hour. So basically, you drink the tea. Now you have an intake of 35 milligrams. And then, as like your body, like it takes out wastes. So by doing that, every hour it could eliminate 12.5% of the caffeine. So write a model here, it says, right? Yeah.
Yeah, not for, yeah. 4.8.
But, oh, okay. I think we were off by a factor of 10. Okay, I'll go back right now. Sorry. So here, all right. So this is the initial amount, right? N naught is 35. R is 0.125. So N is N naught 1 minus this time, right? R to the power of t. So this is 35. 1 minus 0.125 to the power of t, which is this. So N is equal to 35 times 0.875 to the power of t. Okay? All right, so let's graph this one. And I'm going to keep that first equation in there. I'm just going to go on the equal sign and unhighlight it. And here I'm going to put in my second equation. So 35 times 0.875 to the power of t, or x. Now, my windows for this, right? X is the time. So, how many hours? Like 10 hours. Right? And what about the Y min and the Y max? So eventually it's going to go down to 0. And how much caffeine did we start with? We started with 35. This one's 0. And for the Y max, let's just splurge and go to 50. Okay. So now,
So X max would be what?
10.
No, is the Y min?
The Y min is 0 here. So again, we're going to pick points, right? And here we're going to do this way. So it's 1, 2. I have a little bit more room here. Thank you. Yeah. And here we said we're going up to 50, right? So I can make each one of these 5 probably. $25. Really 35 is the highest I need to go. Did you finish? Okay. So when x is 0, it's at 35. Right? When x is 2, it's 27, and so on. Okay, press trace.